Hello everyone, we're team 1 from A5. Our problem statement for SIH 2025 is to design and implementation of solar power dewatering in mining operations. It is a renewable and sustainable technology for mining. So the problem statement here is that in mining operations, usually for dewatering, they use either generators which are powered by the power grid or the ones which are powered by the fossil fuels like diesel. So the drawback is that diesel generators release a lot of carbon emissions into the atmosphere and the uh, pricing is high. So our proposed solution is to create a solar powered dewatering system for mines which utilizes high efficiency solar panels and submersible pumps with smart controls for adaptive operation. So the way it addresses the problem is it enables continuous reliable water removal without any reliance on diesel or power grid, and it reduces mining operation costs and carbon footprint. So the uniqueness and innovation of the solution is real-time optimization based on sensor feedback. So we basically can keep the sensors under the ground. So it can detect the water level which is rising and automatically sends the signal to the pump so it can dewater automatically without any manual labor. So it is also suitable for both small and large scale mines. Next slide.
So the technologies that we'll be using are solar panels. We'll be using two types of solar panels, monocrystalline for better efficiency and polycrystalline as they're more cost effective. We'll be using both of them. Submersible and centrifugal pumps. Submersible pumps are the pumps that will be submerged in the water, and centrifugal pumps to move the water from one place to another. IoT sensors to check water level and pump performance. And then we'll be using microcontroller, so that is the brain of the system. And remote telemetry and cloud dashboard is a future scope that we are keeping as a to store the data of the sensors that we'll be collecting. Methodology, first we'll be going to what is currently going on, the assessment, that is, we'll be checking water table flow and everything. Then we'll be designing to what we noticed during the assessment. Then we'll be implementing the design, a prototype we'll be creating, and we'll be testing that prototype in the remote operation. Next slide. Um, so potential challenges and risks that we might face during this system building is seasonal variability in energy generation, the water chemistry impacting the pump life, and then high initial capital cost, analysis of feasibility of the idea, technically feasible while commercially available, so solar and pump tech, uh, and modular. It operates in both shallow and deep pits, varying sunlight conditions. Strategies that we'll be using for overcoming these challenges are battery backup for overcoming the solar energy generation when the sunlight is low, and using corrosion resistant pump materials to increase the pump life of the pump, and then environmental impact monitoring and regularity compliance.
The potential impact is that it is in safer working conditions, reliable water removal, economically it reduces operational costs up to 40% and minimizes fuel logistics, and it is long-term return on investments, and it cuts carbon dioxide emissions up to 70 to 97% compared to diesel pumps. The benefits are that it reduces reliance on fossil fuels, enhances mining productivity and operational uptime, meets future regulatory, and gives a positive stakeholder community engagement. Next slide. The research papers that we have referred to are solar power in remote mining sites, artificial lift systems for mine dewatering, solar powered water pumping systems, integrating renewable energy into mining operations, the environmental benefits of solar water pumping. We have observed that dewatering is inefficient and costly, especially in deep or remote areas. So using solar power reduces the energy costs compared to the traditional water pumps in farming and fossil fuels. Next. Thank you.